It's a delight to introduce today's speaker, Dan Son from the University of Chicago. Son's interests are very broad, starting with cosmology and all the way down to atomic, nuclear, and particle physics, so that I wouldn't even be able to cover all the great results that he's obtained, but I would emphasize one big theme, which is a part of his research, and that's the connection between condensed matter systems and field theory and particle physics. Historically, that connection has been very useful for both fields, and Son is the one who is continuing definitely the tradition, but also he's taken that tradition to a much higher level. In fact, gravity was never part of that fruitful collaboration, and he realized that many methods developed in classical gravity as well as in string theory can be used to describe some condensed matter systems, and got very interesting results. So he was ahead of the community, mainstream string theory community, by roughly 10 years in that. As a result, he's a university professor in Chicago, having a joint appointment in the Enrico Fermi Institute and the James Franck Institute. And I would like to finish this by personal touch. So Son and some of us in the audience went to the college, in the same college, worked almost in the same group, and he was maybe a couple of years ahead of us, and he was always a subject of admiration and remains so even today. So I'm delighted to have him here.
Oh, thank you very much. It's a great pleasure for me to be here. I have had a great time talking to people here this afternoon. Today I'm going to tell you about some older work that, but the activity in this area is still continuing until now. We have, as I will tell you a little bit later, we have seen some connections between some problems in physics that at the first sight seems to have no connection with each other. I will talk about the physics related to viscosity of fluid, the physics of the Quark Gluon plasma, and connections with string theory, in particular with physics of black holes as seen from string theory. The plan of my talk will be as follows. So first I will talk about the notion of viscosity at the level of undergraduate physics. And then I will change the topics to talk about physics of heavy ion collisions, which are the experiments that are trying to discover the Quark Gluon plasma and study the Quark Gluon plasma. Then I change the subject again and talk about techniques from string theory called gauge gravity duality, and how this technique can help us computing viscosities in a class of system where no other method can allow us to compute almost anything. And then, as the last topics of my talk, I will cover some more recent developments that connect quantum anomalies that are very subtle quantum effects in field theories with hydrodynamics or just fluid dynamics. You will see a connection between another two seemingly unrelated fields. Viscosity was introduced very early in the history of physics by Claude Navier in the beginning of 19th century. He wrote down, he's one of the, so he introduced this viscosity into the, what we now call the Euler equations. The equations that describe the time evolution of viscous fluid is now called the Navier-Stokes equation. If you look at the definition of viscosity in a typical textbook, in this case Wikipedia, you will see that you'll see a picture similar to this one. You have two plates, a typical experiment, thought experiment to measure the viscosity consists of two plates and a liquid or fluid or gas in between. And you try to move one plate with respect to the other. The relative velocity between them is called u, when you set up a relative motion between two plates, you will set up a differential flow of the liquid in between, because the fluid here will near the lower plate will have velocity 0. Here the velocity of the fluid will be equal to the velocity of the motion of the upper plate. The friction force that one has to overcome to maintain this motion is proportional to the product of three variables. The first one is the area of the plate. The second factor is the derivative, how fast velocity changes when you go from the lower plate to the upper plate, dux over dy. And there is a third factor, that is a property of the fluid itself. This factor is called the shear viscosity, or in this talk we will simply call it the viscosity of the fluid. You do the experiment with different fluids and then you get different friction forces because they have different viscosities. Maxwell was the first person who made an estimate of the viscosity of a dilute gas from the kinetic theory. At the time of Maxwell, the validity of the kinetic theory is still under discussion. So he used this, so he's tried to extract physical consequences from kinetic theory, and one of the things that he found kinetic theory can predict was the viscosity of dilute gases. The formula that Maxwell came up with is the following. The viscosity of a dilute gas is proportional to the product of the mass density rho, the typical velocity of the molecules v, and the mean free path of each particle, that is called L. From this formula, Maxwell deduced a consequence that seems to him counterintuitive. That is, the viscosity of a given gas does not depend on the pressure if one keeps the temperature fixed. How one can get this prediction? Suppose I have a gas and then I reduce the pressure by a factor of 2. When I reduce the pressure by a factor of 2, the mass density decreases by a factor of 2. At the same time, the mean free path of the particle increases because the gas is more dilute. So it takes a longer distance for a molecule to find another one to collide with. And from simple geometry, we find that the mean free path increases by exactly the same factor of 2. If the temperature is held fixed, then the velocity of a gas, of molecules, remains constant. This prediction seems so unusual at the time because people at the time, including Maxwell, expected that the viscosity should be bigger if the gas is denser. The viscosity must be somehow proportional to the density of the gas. So this prediction led Maxwell to ask Stokes whether there has been any experiments that confirm the result. Apparently, Stokes told him that there was an experiment that contradicted this prediction. That the result of the experiment seems to indicate that the denser the gas, the larger the viscosity. So in 1860, Maxwell wrote the following sentence. Such a consequence of a mathematical theory is very startling, and the only experiment I have met on the subject does not seem to confirm it. However, he then Maxwell then decided to perform his own experiment. During the next few years, Maxwell, with the help of his wife, designed and carried out his own experiment. And you can still see the equipment that he used to measure the viscosity of air in Cambridge. So here is his equipment. Basically, it's a pendulum type experiment where there are discs that can rotate with respect to each other. Next to this is original Maxwell's desk, and he reported the result in 1865 that the viscosity of air is independent of pressure when the pressure of the air changes from 1/60 to 1 atmosphere. So within a rather large range of densities, the prediction of kinetic theory of gas is correct. So that is one of the interesting occasions in physics where a theorist, a physicist, experimentally confirmed his own theoretical prediction. So before continuing, let me talk a little bit about the somewhat counterintuitive behavior of the viscosity. That one can make it a little bit sharper by imagining that we can turn off we have some dial that allows us to turn off the interaction strength between the molecules in a gas. So when we make the interaction between molecules weaker and weaker, the gas becomes more and more ideal. An ideal gas is a gas where the particles do not interact with each other. In an ideal gas, we would expect should be no dissipation. So the viscosity must be zero. On the other hand, Maxwell's formula tells us that the viscosity would go to infinity because the mean free path becomes larger and larger. So there seems to be a contradiction here. And the way to understand this contradiction is that we are talking here about two limits that do not commute with each other. That we have to specify which limit we take first. The limit where the interaction becomes arbitrarily weak, and the hydrodynamic limit. The hydrodynamic limit is implied when we do the experiment. That is a limit where the distance between our plate is much bigger than the mean free path of the particle. Only when we talk about the physics at length scales much bigger than the mean free path, the notion of viscosity makes sense. So the viscosity, since the viscosity is well defined only when the size of the experiment is much bigger than the mean free path, the divergence of viscosity when the mean free path goes to infinity does not contradict the fact that if we have a apparatus of fixed size, the system will behave like a non-dissipative system when the interaction is turned off. There is actually no contradiction. So let me now jump to another topic, and we will see why this is related to the topics of viscosity. I will describe the physics of the Quark Gluon plasma. So let us remind ourselves that strongly interacting elementary particles like protons and neutrons consist of smaller building blocks called quarks. We can have particles that consist of 3 quarks, and there are particles that participate in strong interactions that consist of a quark and an anti-quarks. These particles are called mesons, and the lightest meson is the pions that appear in cosmic rays. When we increase temperature and density, then we will see a change in the behavior, qualitative picture of the system changes. So imagine that we have a gas of these objects, the hadrons, that are called hadrons at low density. So at low densities, the distance between the neighboring particles are much bigger than the size of the object themselves. One can approximately think about the system as a dilute gas of this bound state of these hadrons. So this phase, this is called the hadron gas. On the other hand, if we increase the density of this gas to the point where these particles overlapped, have a substantial overlap with each other, then it is more convenient to describe the system not in terms of this bound state, but it's much easier to think about these constituent quarks as being able to move freely from one end of the system to another. So one can see that by changing the density, we can change qualitatively the picture from a hadron gas to something that is called the Quark Gluon plasma. It's called plasma because they are similar to the electromagnetic plasma. The particles here are quarks that carries color charge, that are charged under the color interaction. It's called Quark Gluon because the constituents of this plasma are not only quarks but also the particles that they exchange that are gluons.
So is the electromagnetic force irrelevant for the description of this?
So if we have a very big system, then it would be relevant. However, for the system that are created in experiments that I will tell you a little bit later, the electromagnetic interaction normally don't play a big role. They don't play a big role, for example, in thermal equilibration of the system. However, they can radiate photons, and this is one of the way we measure the temperature of the system. When a photon radiates, it is transparent. The system of small size is transparent toward photons. So in reality, the hadron gas, the picture that we have just drawn before, that make a distinction between a hadron gas and a quark gluon plasma is actually in reality is more complicated. The hadron phase, the hadron gas phase, and the quark gluon plasma phase looks very different. But in fact, if one thinks more deeply about the nature of the phases, turn out that in real QCD there is no symmetry that forbids smooth phase transition from the quark gluon plasma to a hadron phase. So this dotted line here may not be a phase transition at all. This is one version of the phase diagram of quantum chromodynamics, which is the theory describing strong interactions. On the vertical axis, we plot the temperature in the unit of mega electron volt. The transition from hadron phase to quark gluon plasma phase happens around the temperature of about 10 to the 8 electron volt or 10 to the 12 Kelvin. This axis is the axis corresponding to the baryon chemical potential, the asymmetry between baryon and anti-baryons. And there is a lot of uncertainty in this phase diagram when we go to finite baryon chemical potential. All these phases here, in some sense, are the result of some theoretical calculations and extrapolation from intuition. On the other hand, the physics near zero baryon chemical potential is pretty well studied by lattice simulation of QCD.
What is this phase transition within the hadron phase?
Within the hadron phase, so there are various things. So when you go from here to here, you jump from the vacuum to the nuclear matter. So you can think about a nucleus as a liquid that is in equilibrium with the vacuum outside. So this is the first order phase transition between nuclear matter and vacuum. And then next to that, there are a lot of speculation about phase transitions from nuclear matter to quark matter, and these are the complicated phases here.
Where would be a neutron star here?
So a neutron star would have a very low temperature and finite density. So the core of neutron star will be somewhere here. Whether it is in the nuclear matter phase or a quark matter phase is not clear. It's not clear at all. The crust of neutron star clearly will be here. Somewhere here. So in order to create and study the quark gluon plasma, there have been a series of experiments starting from low energies and going up to the LHC. So there are two recent experiments that have made a lot of progress in the study of the quark gluon plasma. The RIG experiments, which is here, that collide gold atoms at energy 200 GeV per pair of nucleons, which correspond to relativistic collisions of nuclei accelerated to gamma factor equal 100, and at the collision at LHC between lead nuclei with energy that is one order of magnitude higher than the collision energy at RIG. A typical heavy ion event can be very, very violent. we collide two big objects at very high energies, and there are a lot of secondary particles that are created during the collisions. The process is very complicated, and what one observed are thousands of particles in the detectors. So here are the reconstructed tracks of the particles that are created from collision of two gold nuclei at RIC.
Can you follow each individual particle in that experiment?
So what the experiment measures are the register in the detectors are the momentum of the particles. So they have detector almost 360 degrees with a very large coverage at start, and then they can register the final momentum of these particles. So so all these particles have been created within a very small region in space. And if we look naively estimate the energy density of the initial state, we will find that it is more than enough to put us in the Quark Gluon plasma part of the phase diagram. We have, however, to really identify, to really conclusively say that we have created the Quark Gluon plasma in the heavy ion collision experiment requires a lot of extrapolations, a lot of measurements. So what is the consensus now is that the RIC experiments and the LHC experiments have created strongly interacting medium, and we know that the system of particles that we have created are interacting. This information comes from mainly from two measurements. One is the suppression of back-to-back jet correlation in heavy ion collision. So if we collide two protons, then there are many, in some cases, we will see two jets, highly energetic jets that come out from the collisions. They come out because two quarks inside the nucleons collide and they are deflected with a large angle, and the quark, when the quark move, they form jet, and these jets are usually back to back. In heavy ion collisions, there are many events in which we see only one jet, and the other jet seems to be lost. There is almost a single jet event, or very asymmetric events where one jet carries a large energy and the other jet has a much lower energy. One of the explanation that seems plausible is that the jets are created, that we see are created near the edge, near the border of Quark Gluon plasma or some kind of dense material. When the jets travel, one jet have to travel a short distance through the medium, so they would escape the medium almost intact, and the other jet has to go through a large distance inside the medium, and by the time it gets out, the jet already lost almost all of its energy, and we don't see this as a jet. We see it's a collection of low energy particles that are quite diffuse and not travel in the same direction. The second part of the information indicating a strongly interacting medium created at RIC is the so-called elliptic flow that I will talk about a little bit later. Now, one of the questions that people ask that is related to the elliptic flow is the question about the magnitude of the viscosity of the Quark Gluon plasma. I will tell you a little bit later why the viscosity is important for the Quark Gluon plasma. But let us now concentrate.
Can you tell us where we thermalized at all?
In this
experiment, because to be on the For each diagram, you need to be thermalized, and being thermalized.
So there are indications that the system is thermalized. So one of the thing one can measure is the energy spectrums of the particle that you measure in the experiment. The number of particles as a function of energies. Another quantity one can measure is the number of particles as a function of the number of particles of different species. So these numbers can be fit within a model that consists of very few parameters: the temperature, the chemical potential of the stuff that is created. So if you have a finite temperature, you would see a thermal spectrum of the things that you observe in the detector, and you see the same temperature for all the species of the particle. And then you measure the relative abundances of particle with different baryon number. You can identify the chemical potential for the baryons. So the thermal model of the quark gluon plasma of the heavy ion collision seems to work well. That is one. This is one indication. I think this is the suppression of back-to-back, and the elliptic flow in particular is especially the elliptic flow tell us that the evolution of the system is described very well by a hydrodynamic model. So, which would work if the system is in thermal equilibrium. It's possible that hydrodynamics also can describe some out of equilibrium system, but that we don't know. So, theoretically, it seems that theoretically we don't understand the process of thermalization very well, but one thing we can say is that with the increasing of the energy of the collision, thermalization should become better and better. So at asymptotically high collisional energy, the system should have enough time to thermalize. So let us assume that the system is thermalized and characterized by a temperature. We want to understand if we can compute the viscosity of such a fluid. And here the fundamental theory is well known. It is quantum chromodynamics, and the theory has a very nice properties that it is weakly coupled at high energies. At high energies corresponding to short distances or high temperature, the coupling constant, which is normally called alpha S, is quite small. It's not as small as the fine structure constant in quantum electrodynamics, but would still allow us to do reliable calculation for processes involving strong interaction happening at very high energies. The problem with heavy ion physics is that most of the evolution of the quark gluon plasma correspond to temperature which is of order of 1 GeV. This is exactly where the coupling constant becomes quite large. So in reality, the coupling constant is not small, and computing the viscosity in this regime from the fundamental theory seems to be a hopeless task. So this problem is already known when people try to compute thermodynamics of the quark gluon plasma. For the viscosity, the problem is seems to be even worse. So there is no way to compute the viscosity of the quark gluon plasma in the regime of interest. So in desperation, theorists like myself turn to a class of a different type of theories, and we escape.
So
yeah.
we can conclude that GeV was the temperature trick.
GeV was the temperature that you extract, so not GeV. The temperature you extract from the slope typically is few hundred MeV.
Even less.
Yeah, but in a statistical ensemble like a Bose gas or a Fermi gas, the typical energy of a particle is 3 to 4 times the temperature. So roughly speaking, the average, and so 3 and 4 is just the number of spatial dimension. So it is, roughly speaking, 1 TeV, roughly. So theories turn to another class of theories where things are simpler. Calculation can be done in an easier way. These theories surprisingly came from another unrelated corner of physics, the string theory. In 1997, Maldacena made a conjecture, a very non-trivial conjecture about the duality between quantum field theory and string theory. So he said that there is an object in so-called type 2b string theory called the a stack of D3 branes that I try to depict here as some kind of soap bubble. So when you put a lot of these D3 branes on top of each other, you can describe the object in 2 different ways. In one way, the fluctuation of the object is described by a quantum field theory called the N=4 super Young-Mills theory. The Young-Mills here refer to the non-abelian gauge theory, nature of the theory like QCD, but it is supersymmetric. It is maximally supersymmetric field theory. In another description, it is string theory in 10-dimensional space. In this particular case, it is an anti-de Sitter, 5-dimensional anti-de Sitter space-time sphere. The metric is written here. So here I was trying to depict the anti-de Sitter part of the metric, which is a space with constant negative curvature. So this is a very, this duality, which is now has been subjected to numerous checks, became a very powerful tool for studying the strongly interacting limit of quantum field theory. And why it is useful in the strong coupling limit? It is because of this formula that I'm going to explain now. So the quantum field theory, this N=4 super Young-Mills theory, has 2 parameters. One parameter is the number of colors, which is 3 in the real world QCD, but in this case we can choose it to be arbitrary number. Let's call that NC, the number of color, and the charge of the quark, or the coupling constant, G. So when we do quantum field theory using the usual Feynman diagram technique, the expansion parameter is G squared times NC. When we expand certain quantity in perturbation theory, we expand it in Taylor series over this G squared NC parameter. Maldacena's conjecture put a correspondence between this quantity and a certain ratio of length scale in the string theory side. On the string theory side, there are 2 length scales: the radius of curvature of the anti-de Sitter space and the typical length scale of the string length, the size of a smallest string. And the relationship is G squared NC equal to the 4th power of that ratio of R, big R, over the string length, which which means that if we take the limit G squared NC much bigger than 1, the string theory will become gravity. Why is that? G squared NC much bigger than 1 means that the string length becomes much bigger, much smaller than the curvature radius of the space. When the strings becomes very small, they behave like point light objects, which means that the string theory now becomes drastically simpler. It becomes just a theory of gravity with some matter in it. So we can use the Maldacena's duality to map a difficult regime in field theory, the regime of very large Hove coupling, or the large expansion parameter, where nothing else works, with an easy limit in string theory in which things become just calculation within Einstein gravity. And that has been used, the duality can be extended to finite temperature. And at finite temperature, the situation is very interesting. We can map the Quark Gluon plasma, here the Quark Gluon plasma in quart, because it's a Quark Gluon plasma within a class of theory, including N=4 super Young-Mills theory, in which Maldacena's conjecture works, and some black hole solution to the Einstein equation, of Einstein field equations. The correspondence work for the entropy. The entropy of the Quark Gluon plasma is put into correspondence with the entropy of black hole. We know from the work of Wittgenstein and Hawking that black hole has entropy. So here we put here the black hole entropy is identified with the entropy of the Quark Gluon plasma in the field theory description. Now, the viscosity, there is an interesting part of the story. The viscosity of the Quark Gluon plasma can be put in correspondence with absorption cross-section of gravitational waves by a black hole. This is something I would like to explain in terms of pictures. We have seen that the elementary textbook definition of black holes required us to put two plates and enclose a liquid between two plates and move one plate with respect to the other. But it's from the point of view of theorists, the easiest way to think about the viscosity is actually through gravitational wave scattering. So we imagine that we have some strong source of gravitational radiation and try to shine gravitational wave through the liquid. The claim is that this process of absorption of gravitational waves is sensitive to viscosity. So why is that so? So let us imagine that this is, we have a fluid, and I use some ink to draw a circle in the fluid. And then with my source of gravitational radiation, I shine gravitational wave through the fluid. So when gravitational wave was passing through the fluid, the shape of this circle oscillates between ellipses like this. There are two ways to think about this oscillation. In the GR way of thinking about this process, the geometry of space-time changes when we have gravitational wave passing through the system. So the distance, the notion of distance changes, and the aspect ratio of this ellipse changes. In the more conventional Newtonian way of thinking about the process, a gravitational wave is just the wave of gravitational forces. So we have forces acting on the fluid that pull and push the fluid in different direction and changes the shape of the circle. These two ways of thinking about the same process are equivalent, but using the Newtonian way of thinking about the process, it becomes obvious that the absorption cross-section of graviton must be sensitive to the viscosity of the fluid, because here we are setting up a motion of the fluid where different part of the fluid moves with different velocities. There is this means that the absorption cross-section of gravitational waves is related to the viscosity, and this is the physical essence of something that is called Green-Kubo's formula in statistical mechanics. That is a relationship between the viscosity and a certain correlation function, a certain two-point correlation function, or imaginary part of the retarded Green function of the stress tensor. So this way of thinking about the viscosity actually allow us to use the gauge gravity duality to compute the viscosity of a Quark Gluon plasma dual to a black hole. All we need to compute is to compute the gravitational cross-section, the absorption cross-section of gravitational wave by a black hole. And this actually can be done quite easily, and one can prove a theorem that the absorption cross-section of a black hole is proportional to the area of the horizon when the wavelength of the gravitational wave becomes large. On the other hand, we also know that the entropy of a black hole is proportional to the area of the horizon. So when we take the ratio of the absorption cross-section of graviton to entropy, the area of the horizon cancel each other, but that means that the ratio of viscosity over entropy is something that does not depend on the precise value of the area of the horizon. They cancel between the numerator and denominator. So we found with that the viscosity over the volume density of entropy has a universal value in theories with gravitational dual. So the ratio eta over S within a class of theories, including N equal 4, super Young theory, strong coupling, and some other quantum field theory, has a very interesting universal values. So this result was, I found this result in collaboration with Pavel Kovtun and Andrei Starinets, and we started working in this project when Andrei was a graduate student at NYU, and without him I would not be able to learn all the string theory techniques that are required to compute and the viscosity, and came into this conclusion. So what is interesting about this result is that we now can go back to Maxwell and try to understand the physical meaning of the statement that the ratio of viscosity over entropy density is proportional to the Planck constants. Somewhere quantum mechanics should come into play here, because the right hand side is h bar, contains h bar. So back to Maxwell. Maxwell told us that the viscosity of a gas is rho VL, where rho is the mass density. The entropy density of a gas is, roughly speaking, the number particle density up to some logarithmic factor that we ignore here. So if I divide eta over S, we will find that the ratio is mv times L, where m is the rho over n, which is the mass of each molecule. But I can say that mv is the typical momentum of the particles, which is h bar divided by the de Broglie wavelength of the particles. And so eta over S can be estimated with the help of Maxwell and some quantum mechanics, that it is proportional to h bar times the ratio of the mean free path and the de Broglie wavelength. The statement that in our theories eta over S is equal 1 over 4 pi, h bar divided by 1 over 4 pi means that the mean free path of these particles have to be as short as the de Broglie wavelength of the particle. So,
sorry, but in the final analysis, couldn't you have written this formula with no black holes, because eta greater than what's given by your formula is probably meaningless? No, the lower formula. Eta probably cannot be greater than entropy in some very crude quantum mechanical estimates, no?
No, eta typically is, for liquid, is much bigger than h bar over 4 pi times S.
Or the other way around.
Yeah.
So it cannot be smaller.
Oh, cannot be smaller. This, we are here seeing a limit of the kinetic theory. This estimate assume already that the mean free path is much bigger than the Broglie wavelength.
Without dropping all these black holes, can you somehow understand that eta cannot be smaller than entropy or something?
Even now we cannot conclude that. All we can say is that within the kinetic theory, eta over S cannot be much smaller than 1 over 4 pi. We know examples from gauge gravity duality of theory where this is equal to h bar over 4 pi within a class of theory. So we don't know whether we can push that to much lower values.
Shouldn't it be obvious from common sense? This is what I'm trying to ask. Shouldn't it be obvious from common sense?
From the common sense,
it would be much smaller than entropy.
Common sense. If common sense means extrapolations from the kinetic theory, I would say yes. Although nothing can be ruled out, because there can be, when the system is strongly interacting, we cannot use kinetic theory anymore. And so anything can happen. All the examples that I know seem to indicate that this eta over S cannot be much lower than h bar over 4 pi.
What happened to h bar before you had eta over S equals h bar?
Oh, you just left it out.
Yeah, I put it h bar over to 1. but it should be there.
So there are no claims that this is a lower bound? I thought...
There was a claim. So in the beginning, Pavel, Andrei, and myself speculated that there is an inequality sign. Later, people found examples of a theory in which, if you compute 1 over n correction, it has a negative sign. And then there is a question whether you can go to small n and then make it as small as you want. And within this, of course, you are going, now it's more speculation rather than. So we know example of theory where this is slightly below that. Yeah, 1 over n below. So how do we hope to determine the viscosity of the quark gluon plasma? We look at collisions with non-zero impact parameters. So imagine that we have 2 nuclei. The most interesting event for determining the viscosity is when they do not collide head-on, but they collide with some impact parameters. So initially the quark gluon plasma, or the liquid that we form, has a shape that is not spherical. So this region of hot material will expand, and one can understand how it expands. It actually will expand faster along the shorter direction of the quark gluon plasma rather than along the longer direction. And you can already almost feel it if you have watched movies when people try to blast through a door with plastic explosive. They shape the explosive in a pancake shape, hoping that it will expand along the shorter direction of this pancake instead of a longer direction. And it's happened that way because the gradient of the pressure, which determines the force acting on the liquid, is bigger along the shorter direction rather than along the longer direction. So by measuring this, so this has been measured, the distribution of energy of particle that you measure has a dependence on the angles. Now, this can be also the effect of viscosity on the azimuthal asymmetry can be understood qualitatively. If we put in viscosity, then it will try to reduce the magnitude of the effect. Viscosity try to put friction between different parts of the fluid moving with different velocity. So by simulating the quark gluon plasma using hydrodynamic simulation, people have been trying to come up with a value for the viscosities. So there are a lot of uncertainties. That's why one of the uncertainties led to the fact that there are 2 graphs here corresponding to 2 different initial conditions that people found, and there are some experimental correction one has to make, explaining why there are 2 curves with dots here. But the result that people come up with seems to indicate that this ratio eta over s for the quark gluon plasma is quite small. It's much smaller than the than 1. It's not too far away from even h bar over 4 pi. So here again I put h bar equal to 1. 1 over 4 pi is around 0.08, and it seems that that this eta over s for the quark gluon plasma can be quite close to this value. So we don't know whether what lessons to draw from here. It might be just a coincidence. We know for sure that the quark gluon plasma, the QCD, cannot be described by just Einstein gravity. The dual theory of QCD has to be much more complicated than that. But for some reason, the quark gluon plasma, in particular the viscosity of the quark gluon plasma, the ratio of viscosity over entropy density seems to be quite close to 1 over 4 pi. So people now talk about the quark gluon plasma created at BRIC and LHC as SQGP, where S may stand for strongly coupled.
What happens in a superfluid?
In a superfluid, you have the viscosity of the normal phase. That is actually
applied to the super component. To the superfluid component?
No, the superfluid component doesn't, you cannot have associate the viscosity with the superfluid component.
It's zero, no?
The only viscosity you can associate it with the superfluid helium is the viscosity of the normal phase, and then within this two fluid model, the entropy is also carried by the normal phase. So one can look at the ratio, but it will.
So superfluid component will have zero entropy also, so
yeah,
it's fine.
So,
Your
yeah.
formula is okay.
Yeah.
Okay.
But in fact, you can. I believe you have to sum up the two here to get the real entropy. So
is it also close to 1?
it's close to 1 instead of 1/4 pi if you do that for helium, superfluid helium. Actually, for helium, you can look at you can ask where the minimum of eta/S for helium is, and it's not in the superfluid phase, it's in the normal phase. So the first measurement of the viscosity has been a big event in the history of the research in quark gluon plasma. In 2005, BNL, Brookhaven National Labs, issue a press release in which they say that the degree of collective interaction, rapid thermalization, and extremely low viscosity of the matter form a drake makes it the most nearly perfect liquid ever observed. So this statement of most...
In connection with the comment before, the most nearly perfect normal liquid.
The most nearly perfect liquid, that's
normal
what they
I'm
say.
Saying it's normal liquid, because a superfluid is even more perfect.
The superfluid we have perfectly in some experiment, namely the flow through the pipe, but we have like a normal fluid in
So what I'm saying is that this refers to normal fluids.
This refers to normal fluid. So we have to say what is perfect. So here perfect refers to a viscosity, and with the superfluid we have to refer to viscosity of the normal component.
Right,
but there is
arbitrarily low at low temperatures. So
the viscosity of helium actually increases when the viscosity of the normal component of superfluid helium actually slightly increases when you lower the temperature.
I'm talking about the amount of normal.
The amount, the amount.
Zero.
Well, the density, the normal density goes to 0, but the mean free path actually increases. Yeah. So that makes the So the extremely low viscosity here actually means something referring not to the absolute value of the viscosity, but because if we estimate the absolute viscosity of the quark gluon plasma, we find a value that is much bigger than anything except maybe except viscosity of glasses. So in terms of absolute term, quark gluon plasma is very viscous. And that's because the density of entropy, when we talk about the low viscosity, we have to divide the viscosity over the entropy density to get a small value. That's what they mean in the Brookhaven National means when they issue this announcement. So I have very little time left. Let me quickly talk about one particular new development, relatively new development related to the physics of chirality in hydrodynamics. So chirality in relativistic hydrodynamics. So holography has helped us discover new effects in relativistic hydrodynamics. This effect has been overlooked in all previous treatments and can, roughly speaking, thought about as an effect of chiral separation by rotation. So it's very interesting because this effect has a deep connection between with quantum field theories, with quantum anomalies in quantum field theories, with Chern-Simons theory. But on the other hand, it is an effect happening at finite temperature in the fluid. That is, seems to be should be describable by classical physics, not quantum physics. So this has been first discovered accidentally by a group, by several groups, looking at the physics of rotating black hole with R-charged black holes that seem to be very unrelated to this question. But through gauge gravity duality, it maps onto a statement about hydrodynamics. So, in very rough formula, roughly, we can think about example of QCD, that is theory of quark and gluons with massless quarks. The masses of U and D quarks are pretty small. Let's imagine that they are massless. Then the quarks can be classified by helicity, left-handed quark and right-handed quark. The left-handed quarks have spin pointing opposite to the direction of motion, and right-handed quark have spin pointing along the motion direction. So we can look at the current of these quarks. There is a left-handed quarks and right-handed quarks. There is some conserved chiral charges, the number of left-handed quark minus the number of right-handed quarks. Here I grossly simplified QCD. In fact, there are some chiral charges that are conserved. Normally in hydrodynamics, the currents of a conserved charge is due to advections and to diffusion. But in hydrodynamics of QCD, turn out that there is a vorticity-induced current. When we rotate the system, suddenly there is a chiral current that move along the direction of along the axis of rotation. So to illustrate the strangeness of this result, let's imagine that the same thing happens in our ordinary life. So this effect would correspond to the following things in our ordinary life. Let's imagine that we have a cup of water, and then we drop sugar onto this cup of water. We know that sugar comes in two different helicities, left and right helicities. One we can digest and the other one we cannot. Let's put both of them into the cup of water and then rotate this cup of water. And we can ask the question whether the two helicities of sugar will separate along the direction of rotation.
No, they will not.
They will not. However, if we do similar experiment with the quark gluon plasma, the effect of quantum anomalies in QCD would tell us that quarks do separate. So that is one of the results that was obtained by using gauge gravity duality. It's possible now to understand this effect purely from more conventional methods of quantum field theories combined with hydrodynamics, but it was first found using gauge gravity duality.
Why might you think that the sugars would separate?
Wouldn't separate. So there are several levels of the answer to this question. So at the physical level, if you have a screw that rotates with respect to water, it will move. But if you move the water and then wait long enough, then the screw will rotate at the same velocity, at the same angular velocity as water, so it will not move. You can also do a more mathematical, you can try to write down the equation of hydrodynamics and ask whether you can put in a term in the hydrodynamic equation that corresponds to this separation, and that would violate the second law of thermodynamics if you try to do that.
What do you mean by quark separate?
Quark separate means the following. When you write down the I mean exactly that. So if you have a if you have a rotating piece of quark gluon plasma, there is a contribution to the current of quarks that is proportional to the axial current. There is an axial current contribution that proportional to the rotation velocity times some chemical potential. Yeah. Okay, so there are some hint in the RIC and LHC data that people believe, some people think might be related to this effect, and I will not be talking about that. So let me conclude. There are surprising applications of string theory techniques, which give us some new point of view on strongly coupled gauge plasmas. We can think about Quark Gluon plasma as a black hole, viscosity as graviton absorption, even when the correspondence between these quantities are exact only within a quite restricted class of quantum field theories. It seems that the way we think about this correspondence is useful in a larger context, including the Quark Gluon plasma QCD. The gauge gravity duality suggests the smallness of eta over S is a property of strongly interacting systems, and it has given us new insight on the role of anomalies in hydrodynamics. Thank you very much.
Questions?
Am I allowed to?
Oh yes, absolutely.
Because last time you forbid me to. So, this result always, I don't know, I was always amazed by this result, that this viscosity, that there is this bound or an estimate. But on the other hand, I was always annoyed by the way you derive it, all these dualities, Maldacena. This is much simpler than all those gravities. I mean, the result itself, couldn't you play with some strongly coupled scalar field or whatever and deduce a similar bound somehow?
Well, the exact number 1 over 4 pi somehow nobody, we were not able, and I don't think anybody has been able to show that within this class of theory, eta over S is equal to h bar over 4 pi.
Understanding of where this, of why we cannot lower viscosity much below entropy. There must be some simple, you understand?
I think I understand, although I have been thinking about that for somewhat too long, so that frustration goes away. I got used to having forced to use gauge gravity duality to derive a result that doesn't seems to not require any, should not require any gravity. So we are making a statement about just simple quantum field theory, just simple theory without gravity. Yeah, so I'm not sure how to do that.
Maybe lattice simulations, people could discuss something like that in a strongly coupled regime.
Of QCD?
Yeah.
At finite temperature, you can try, but there is an uncertainty, inherent uncertainty in lattice simulation. Lattice calculation is done in Euclidean space with compactified imaginary time, while the viscosity refers to correlation function in real space. How to go from one to the other requires certain art instead of science. And so
also, if you want to do finite chemical potential, I don't think it's easy. The lattice.
It's hard even for thermodynamics. Yeah. So even with temperature, the viscosity from lattice has a error bar that is of the same order of magnitude as the value itself.
But when you form the quark gluon plasma, is it just inertially confined and it just flies apart, or is it actually confined by the strong force field?
It's not confined.
It's not
confined. That's why it's so hard to study it. It lives for a very short time when we measure the energy of the particles that are in the final state of the decay of that of some initial hot plasma.
Well, it's the energy that's not confined. The color stays, it must be neutral. The color is confined.
The color is confined, yeah. The color, we know, should at the end, this whole system is color neutral.
But it cools down and then it becomes back hadrons.
Yeah, it comes back to hadrons. And, yeah.
By the way, you said in this collision you form the Quark Gluon plasma, but it's only if the collision is central enough.
only if the...
But I mean, you explained how you go to finite impact parameters. But of course, if you go to
peripheral
parameter, you miss, right? So I guess only a fraction of the events in the ion collisions have the signature of the plasma. It's not just 100% of the collisions, right?
Yeah, it's not 100%, but I'm not sure I know what is the minimal...
People trigger on something to say, well, I look at an event which presumably has the plasma.
So they look at the way that they determine the impact parameter is through the final multiplicity. So there is a multiplicity like, yeah, the multiplicity is like 10,000 for central event, and then you go to, when you go to like few hundreds, probably you would say that it cannot be thermalized, but within a finite fraction of the maximal multiplicity, you select event, yeah, by the multiplicity.
When you do the duality, you always have essentially an infinite area black hole. It's very large. So,
yeah.
Is there any clues instead in looking at the global
finite
coordinates in ADS where you know that there is a phase transition?
But global coordinates in ADS correspond to having a system on finite on a sphere. Finite volume.
Finite volume, so there you can play with the ratio of temperature over volume, temperature times volume, because there you expect, at least from the dual, you expect a phase transition at some point.
This phase transition is a phase transition already in conformal theory.
In conformal,
yeah.
So it doesn't have, it's not the...
it's not the phase transition that we have here.
Can one hope to see that transition?
Maybe on the lattice, but not at RIC, because at RIC we have a finite size system, but it's not that the system is confined in a. So there, you know, you have to confine system on a sphere and impose condition of color neutrality on the sphere. I don't know how to do that in real experiment.
On this anomalies in the hydrodynamics. Does that effect depend on the temperature of the plasma, or?
Yes, so the coefficient, so I forget the so here the vorticity induced current, for example, this C is completely determined by the coefficient of anomalies and chemical potential and temperature. So I can look up the formulas. I don't remember it by heart, but there is this.
So it's more than just anomaly.
No, it is just anomalies. It's remarkably interesting, because here you have a number that is not a dimensionless number. It's something that multiplied chemical potential and temperature. On the other hand, you know exactly the functional form of this coefficient as a function of chemical potential and temperature. And the coefficient in these polynomials are just related to the anomaly coefficient. It's quite...
So anomaly coefficient is dimensionless?
They are dimensionless. They're 1 over 4 pi square. Yeah.
Then the other factor is the
just the chemical potential and temperature. And you know exactly the functional dependence on this number, on this. How do you get this functional dependence? So there are different ways. One way, the original way that we found, was to insert this into hydrodynamic equations and try to make it consistent with anomalies in hydrodynamics in background metric and background field, and make this consistent with anomalies and second law of thermodynamics. It's possible to do it. Now people, I think, have a better way to do that. They look at the a static equilibrium in a background field, background metric and background gauge field, and from the properties of the functional of this partition function at finite temperature and chemical potential and anomalies, they can find these coefficients. Some kind of anomaly matching between, we have here seen an anomaly matching between microscopic theory and the hydrodynamic theory.
But the microscopic theory here is what? Is QCD or is it gravity?
It can be any, it's a field theory. Doesn't have any gravity. Gravity is, there is a role also of gravitational Chern-Simons, but gravity is a background. It's not a gravitational anomalies, but gravity is background. Yeah.
So we had quite a few questions. Let me propose to continue this very interesting discussion on 6th floor with wine and cheese, and let's thank Sean again for this.
Thank you very much.